Iftach's going to tell us about parallel repetition for arguments.
Yeah. So following Ariel, I allowed myself to change the title than the one written in the program. This is more advanced, more general theorem that we recently proved. So I'm going to speak about type parallel repetition theorem for partially simulated argument. I'm going to explain partially what it is. Via smooth KL-Divergence. This is a joint work with my former student Itai Berman and my current student Eliad Sfadia. So this talk is about, what to say that this is, thank you for staying, even Muli is here, but now, now it's no longer true. So, I didn't say. So, because even in Tel Aviv, it's not that easy to catch him. So, anyhow, so this talk is about hardness amplification. And what is hardness amplification? This is one of the most basic tasks in computation, the study of computation. Turn a weakly hard primitive into hard one, okay? Numerous examples, you know, if you're a cryptographer, so weak to strong one-way function or puzzles. If you're a complexity theorist, then worst case to average case reduction of functions for languages. And if you care about protocols, this is reducing soundness error of interactive proofs, single prover, many provers, and the focus of this talk is what's called interactive argument or computationally sound proofs. These are proofs the soundness only holds against polynomial bounded proofs. Good. So what are interactive arguments? You all know what they are, but just let me very quickly. There's a prover and a verifier and the statement. The verifier either accept or reject. And we said that this protocol has beta soundness if on invalid statement and arbitrary efficient prover, the probability that it makes the verifier accept is at most beta. So typically we would like beta to be negligible, but sometimes don't get it directly, and we get beta, say, equal half, and then we want to amplify. So what's good about, apart from being for interactive argument, being interactive argument, which you care about for proving something about the language, but if you think about it, then the security aspect of many security aspects of many cryptographic primitive can be cast as the soundness error of interactive argument. For instance, you have a commitment scheme, so the binding of the commitment can be cast as a soundness error of interactive argument or related interactive argument. And therefore, if you find methods to improve soundness error of interactive argument, it immediately implies methods to improve, say, the security of the binding of statistically ID commitment. Okay? So we are more caring about hardness amplification. Interactive argument is more than only for argument. It's also for other primitives. Good. So the focus of this talk is amplification of interactive argument, namely to find a generic, hopefully simple transformation that reduce the soundness error of a protocol for argument. So we're starting with some argument, say a soundness error is 1/2, and you want to transfer it to different argument to soundness error, say, is negligible. Okay? This is the goal. And again, we'd like to have a generic transformation that applies to any argument, and to maintain the properties of the original protocol. You don't want to throw away the protocol and give a new protocol. Rather, we'd like to have a transformation that is almost does a very simple thing, maintain additional properties of the protocol. So, you know, ask any kids, and you tell you that if something is hard, somewhat hard, doing it many times becomes very hard, right? We all know it. And in particular, it means that what's known as repetition, or that you repeat if you want to prove something, just prove it many times, independently. So the verifier is independent. Okay? And the most natural way to do that is via what you call sequential repetition. Namely, the prover prove that verify that the statement is correct. When it ends, he prove it again, and only if he succeeds in all these sequential interaction, the verifier accepts. Okay? So sequential repetition reduce soundness error in the you notice the time, anyhow. So in almost any computational model, okay? It always works, okay? And in optimal rate, in the rate that it's easy to see that you cannot improve better than 1, if the original soundness error was 1 - epsilon, you cannot hope to get more than 1 - epsilon to the power of number of repetition. So sequential repetition is the solution, very simple, everything is great in any computational model, but as you can see, the disadvantage is the round complexity blows up. Good. So why not do parallel repetition? Okay, this is the second most natural thing to do. And as you see, it's definitely preserved the random complexity, okay? So the question is, does it improve security, right? We expect it to improve, but the very surprising question, the answer is that not in general. Okay. So there are protocols which have soundness error 1/2, and you repeat them many times in parallel, and soundness error remain 1/2. This is the very nice example of counterexample of Bellare-Impagliazzo-Naor from 97. So I describe it using safe, but you can think that safe are commitment or whatever you like, or encryptions. So the verifier flips a bit and puts inside a safe and sends the safe to the prover. Okay? It's a stupid example, but it does show what it should be, the counterexample. So, and the prover should put a different bit, B prime, and send it over to the verifier. Now the verifier sends the key to the prover sends the key, his key, to the verifier. The verifier opens the safe, because he got the key, and checked whether B prime equal B. And not only that, he checked that the safe he got back from the prover is not the same safe he sent to the prover, but otherwise there's a simple reply attack. And if this is the case, he accepts. So it's easy to see the only thing that the prover can do is send, say, a constant value or random value. He cannot win more than probability 1/2, but he can win probability 1/2 by just simply putting a random value. Okay. So this is the example. Now let's repeat it twice in parallel. Okay? So two independent verify, put two independent bits inside the safe are sent to the prover, and what the prover does, those of you who never seen this example, No. Okay, so what do I do? Switch. So the switch. And now the verifier sends the keys. No, the answer is clear, the prover switches the keys as well. And easy to notice that both verifiers accept if the first bit is equal to the second bit, which happens with probability 1/2. And notice that each verifier is happy because the safe it received from the prover is different from the one it sends. Okay, so again, soundness was 1/2, you repeat it twice, soundness is 1/2. And this can be generalized to any number of repetition. And more than that, Pietersen and Willstrom showed that there exists a single protocol such that for any polynomial number of repetition, the soundness error remains 1/2. It's not like that if you repeat enough time, then there's issue of communication complexity. No, the single protocol, any number of polynomial repetition, soundness error remains 1/2. Yes?
So when the prover is all powerful, this would not be a counterexample.
Right.
Right?
Right. So it's only because the limitation is the prover is computationally bounded. The counterexample doesn't go, and for good reason, because parallel repetition does work for single prover, like what's called all powerful proofs. Okay. So parallel repetition does improve soundness in many, many interesting cases. Actually, probably in most cases that most people here care about. Okay. So free message argument, this was shown by the same work by Bellare-Impagliazzo-Naor. Public coin argument, where the verifier simply sends random coins in each round. This was first shown by Assad, Pass, Pietersen, and Willstrom. Improved by Chang and Liu, and then a simpler proof with the same optimal result by Chang and Pass. And as you said, it's also true for single prover proof, namely the original soundness error holds against all powerful prover. Also for two prover proof, it's more complicated, started by Raz and an improvement by Orens and Rao, etc. And more related, the work here is for the random termination variant of any argument, and next line I'm going to explain what it means. This I showed 10 years ago. And also for partially simulated argument, this is a generalization of such argument considered by Assad, Pass, and et al. And finally, if you take the original argument and compile it using FHE, then parallel repetition also works. But this is a conditional result. You need to assume fully morpho encryption. And more than that, you basically ruin the original protocol. So if the original protocol, say, was fair, the new protocol is not fair any longer. Okay, so the focus of this talk is this random termination variant. So what it is, you're getting any argument, okay, M-round argument. And the new verifier, you just change the verifier. The new verifier does the following in each round, you flip a coin. And probability 1/m is 1. And if it's 1, it halts and accepts. Okay? Second round does the same. Flip a coin, probably 1/m, it's halt and accept. with constant probability, it reaches the end, and therefore it does like what they accept if the original verified. So it's almost the same protocol, okay? I slightly change the soundness error, slightly change the verify, but all the protocol is almost intact, okay? If it was fair, it's fair. If it was zero knowledge, it's zero knowledge, whatever you like. And I showed 10 years ago that parallel repetition of whatever protocol argument you started with, if you do this trick, then parallel repetition does improve soundness in exponential rate. The downside, that exponential rate is not the one you like. You would like to have 1 minus epsilon to the k, like in public coin or free message argument, etc. But you pay a factor of, in the exponent of m to the 4 over epsilon, meaning that you need to do a lot of repetition to make it work. Okay. So the goal of this talk is to improve this analysis. The same argument, I don't touch the argument, only the improved analysis. Good. So our result will give a tight analysis of parallel repetition of random-terminating variant, and we improve it to 1 minus epsilon, not to the k. We pay a factor of m in the exponent, rather, so it's m over cube over epsilon improvement comparing to the previous result.
So 1 minus epsilon is the soundness of v tilde.
Yes, of v tilde, yes. But you think about epsilon and cont, it's almost the same, yeah.
Can you remind us what m is?
M is the number of rounds, sorry. M is the number of rounds of the protocol. Okay, so again, let me do it again. So m is the number of rounds, and then the verify halts probability 1 over m in each round.
Don't you need like smaller than, like 1 over 2 or something? You're ruining it. Does it seem like
Again?
up to constant factors, right?
Ignore constant factor, yes. Ignore constant factor.
Is the m necessary? You said the m is necessary?
Wait a sec. So omitting constant. And generalized to what's called partially simulated protocol, almost. I mean, I'm going to say something what was partially simulated protocol, but it's almost generalized to the additional requirement for the original definition. And I think not less important, we developed new tool to analyze what we called, sorry for the name, many rounds could embed an execution. I'm going to explain what it is through the proof, and we believe that this tool is rather, such distribution are rather natural, and we hope that this tool is going to find additional application. And for Tzvika's question, this M is essential. We give a lower bound showing that for random termination variant, this M is essential. There is a protocol that only improves like that, 1 minus epsilon to the k over m. A different question is, can you do a different transformation, not to do the random termination? But if you go for the random termination, this is tight.
But you have a formal sense.
No, but so, yeah, so if you have a protocol, you start with a protocol, okay? You consider it random termination, and then you repetition, okay? You think that the epsilon between the original protocol and the new one, the random termination, almost the same, okay? The error, soundness error is almost the same. So you start with the protocol, you do the random termination, do parallel repetition, then the soundness error is the best. This is the optimal. If you start with the protocol, do different tricks, say do fully homomorphic encryption on the protocol, then you do parallel repetition, you get a better, you know that you get a better result. Okay.
But Iftach, this is essential no matter what the probability is of the termination, as long, right?
No, it should be 1 over m.
No, but you can go 1 over m squared, maybe. No,
it should be, if it goes, so it doesn't work at all. Okay, if it's 1 over m squared, it almost never halts, and then you're dead. Okay, should be 1 over m. 1 over m seems to be the optimal. But we show if you 1 over m, it's easy to see that you have to go for 1 over m. Okay. And if you go for larger, then the soundness error, it's always halt, then there's no soundness error. I mean, and you go for a smaller one, then you don't improve. It's the same like the original protocol. So 1 over m is optimal in this.
So Iftach, the fully homomorphic encryption transformation is non-black box with respect to the protocol?
It's non-black box.
So you could ask the formal version of your question, can you do something better?
In black box, right. Or unconditional, there tend to be unconditional result, yes.
No, but public coin, we know that it works.
Public coin works. But
keeping the resulting thing public coin.
So, but if it's public coin, you don't need this result. You have a public coin already. Public coins work immediately. So we can have, yeah. So FHE doesn't seem like the right solution. For me, it's because it's conditional, but again, conceivable because of black box.
Is there any concrete application? I mean, of course, it's interesting as a general statement, but is there any instance that we would like to amplify? Like any?
So the only instance I'm aware of, I'll be happy if you have more, I should ask you before actually, is the only way we know to amplify, say, statistically ideal commitment in a round preserving Manning is using this. So if you want to amplify statistical ideal commitment and you have fully homomorphic encryption, then it doesn't make sense. Probably you can use it to get statistical ideal commitment to begin with. But if you have statistical ideal commitment, the only round preserved reduction is via this manipulation. Good. So how do we prove that? So I started show that more general paradigm to proving parallel repetition of protocol, etc. And then I'm going to show where it's failed for arbitrary protocol and what goes good for a random termination one. So the general paradigm is via lifting, as Yael said yesterday. I had this stupid comment, why lifting? It's indeed lifting. So why is it lifting? So assume you have a protocol. So this is not random termination, arbitrary protocol with soundness errors 1 on epsilon. And assume some pk star wins the k-fold game with probability more than epsilon prime. Think that epsilon prime is very small and 1 over epsilon is almost 1. And we'd like to prove that this cannot be. We'd like to use this k-fold pk star for building p star that wins a single game. And why is it lifting? Because pk star might win probability 1 over a million. It's above than what it should have, but it's very, very small. And p star should win probability almost 1. So we should lift this very small probability to get a very high probability. And this is first, it's heavy lifting, typically. And also, it requires something non-trivial. It's not like reduction that you take something, plug it in, and you get the result. No, you take something, you work very hard, and then hopefully you get the result. Okay? So you have to lift very small probability, which is above than what it should have, to very high probability. So the way it happens both in the single prover and in the multi-prover, it's slightly different, but in a nutshell, or in a bird eye view is the same. So we have this k-fold prover that does too well on a k repetition, okay? And you would like to use it to win a single repetition. So what do? So a single instance. You have you pick one of the verifier at random, and this verifier is going to be played by a single instance verifier, okay? And the other verifiers, you have to play by yourself. So in other words, the new provers is emulated the k-fold prover and the rest of the verifiers. The honest verifier, without knowing that, is playing actually the if verifier. Okay. Now, when this if verifier is sending a message, you forward it to the k-fold prover, but you're expecting k question, not a single one. So you somewhat, and this is the crux of the issue, you somewhat choose the rest of the questions, feed them to the prover, he give you k answer, and you take the if of those and send it to a verifier, and keep on. Okay, so all the issue in this random termination proof, or in this parallel repetition proof, is how to choose these emulated verifier questions. Okay? You can assume with that sort of generality, in this case, that the prover is deterministic. So everything is deterministic, but the answers of the emulated verifier. Okay. How much time do you have? You shouldn't ask. We see you're very liberal. So, okay. So how do you choose them? So the basic idea is very, very simple. Okay, you get the first question from the real verifier, which in your view is the if message of the if verifier, and then you sample a random Unix execution consistent with this message. Okay, you choose all the other methods of the verifier in all rounds, not only in this round, but also in future round, till you get a random Unix execution. Maybe you have to do it many times, but eventually you do. You'll get a random Unix execution whose if message in the first round is this one got from the real verifier. And then you set the first round message of the emulated verifier to the method sent in this winning execution.
You emulate also the ith verifier in rounds 2.
Right. I emulate also the ith verifier, and this is the issue, that you cannot always do that. Okay? You emulated also your verifier, which is rather easy, but also the emulated verifier. Without his agreement, you cannot say, just wait a minute, let's tell me what you do in the future. No. How can you? So sometimes you can, sometimes you cannot. Okay? Let's one sec. If you can, great. If you're unbounded, who ask about unbounded can. This is what happened in unbounded prover. You can do that. This is why parallel repetition of proofs go through. So let's do, okay. So is this a good attack? Yes, in any model, okay, if you manage to do that. But can it be carried out? Depends. Sometimes you can. If it's unbounded proof, you can, because you are unbounded as well. If it's public coin, you can. If it's under fully homomorphic encryption, you can. But generally, you might not. So let's move to public coin case, which is the case you can, because what happened in this attack, the verifier sends just random coin. You should send, you now in the emulation step. You're going to choose a random continuation. If it's winning, you're going to pick it up. You do rejection sampling. Otherwise, you do it again. You continue, and know that you need to sample the next messages of the real verifier. But in public coin, it's very easy because the messages are simply independent random coin. So you can do that very easily, and that's all. So in public coin, you can very easily implement this rejection sampling. Good. So I'm going to soon explain what goes on in non-public coin. You can actually, some of you already noticed that, but let me before that, say something about how you analyze this Fourier attack, okay? So that's one thing about notation. You can think about all the messages as a matrix. This is the first message of all K verifiers. This is the second message of all K verifiers, etc. And one of these columns is the one sent by the real verifier. Okay? And W is just an event over this. Everything is deterministic beside the messages. W is the event, the winning event over these messages, namely the case where all verifiers accept. Okay? So now we have a matrix of all the messages sent by the K-fold protocol in all the M round. Good. So the task is, given the J method of the I verifier, you need to sample, in this term, you need to sample from this distribution, namely you need to do the random matrix that is consistent with the path, consistent with the ith method in this round, and is a winning, matrix. Okay? So this is the task. In this matrix term, this is the task in end. Okay? This is what you need to do. Okay, it's nothing. That's notation-wise the same like what I just described. Good. So how do I analyze the success probability of this attack? So first we describe what is we call the real distribution over this matrix induced by the attack I just described. Okay, random quotation, etc. And now we also consider what we call the ideal distribution. It is just a random winning matrix. Okay, a random winning matrix, a random transcript in which all verifiers accept. And note that the only difference, these distributions are always the same. If you rewrite them, the only difference is that the ith message in the real execution, or in the real distribution, is chosen uniformly by the real verifier, where in the ideal execution, this ith message is chosen condition on winning. Okay? So only the difference is the way the ith message is chosen everywhere. Okay, so now we look at ideal. Ideal is very simple. In particular, in ideal, all verifiers always accept. So if you manage to show that real is close to ideal, it means that also in real, all verifiers always accept, namely, in particular, the ith verifier accept, namely, the attack succeeds. Okay, so this is a very nice paradigm, probably used in many places in crypto complexity theory, to find a different distribution, which is typically easier to analyze, very easy to understand what's going on, and then to compare the real distribution and the ideal distribution. So early work of us at the time.
It's not like too close. What is the distance? Okay.
So Asedal actually measured the statistical distance between the distribution, and this yields untight result. Okay, and my early work on random-termination also considered the statistical distance. What Chang and Pass did in really beautiful work, they bound the KL-Divergence between distribution. And because of bound the KL-Divergence, which is better measure for these settings, they get a tight result. So what is the KL-Divergence? Very roughly is the expected log ratio between the distribution. The expectation is important, is taken over the left-hand side of the distribution. I'm fine?
Five more minutes.
Okay.
We're talking
go back. I mean, are we supposed to understand what this W is in the previous slide?
W is the winning case. The case that all verify except. W doesn't matter this term. That is small. But W is the event where all it's a winning transcript. All verify except in all executions.
Take it on pivot. I mean, in the real and the ideal.
W is everything is defined. That's a transcript. W is basically a subset of all possible transcripts. Okay, you get a transcript, you know if it's winning or not. Right. So W is just a subset of possible transcripts.
Yeah, but when you talk about its probability, what do you mean?
Oh, good. So sorry for that. This probability with respect to the case where the prover wins. Okay, this probability of a win of the K-run prover. It's not with respect to our deal, but actually with respect to the uniform distribution. Good. So W is the event with respect to the uniform distribution that the K prover wins, and which we assume is too large. Okay? Good. So once this probability gets low, you get a worse result, and you should expect it. Eventually, if the provers win only in probability 1 or 2 minus 1 minus epsilon to the K, there are such provers, namely the one that play independent of each of the execution. So you have to play this winning probability. The smaller it gets, your result gets worse, and you expect that.
And the more provers you have, the better the band?
The more repetition you have, the better the band. Sure, because you repeat more, you expect it to improve better, right? Good. So again, this value does not really matter for now. That's the key issue is that we bound KL-Divergence and not statistical distance. Why KL-Divergence? For several reasons. So first, KL-Divergence was used, I think, in cryptography in similar setting many times. I think first work I am aware of is a yellow Astad from 91. And very roughly, sorry for those information theorists among you, it's more subtle than statistical distance, particularly there are settings where statistical distance is the same for two different distributions where actually it's a very different case. So when you have bound of KL-Divergence, you know more about the actual distance between the distribution. Second, KL-Divergence, the chain rule, which is extremely useful when dealing with the distribution induced by protocols, okay, which are iteratively defined. And the third, what's also very, very nice about KL-Divergence, is it's asymmetric, because we take the expectation with respect to the left-hand distribution. And very roughly, again, you need to understand more. It suffices to understand more about P and not that much about Q. Okay? Well, in our case, P is ideal, which is very simple. We really understand it. Q is the real distribution, which is a mess, which you don't understand. But because it's KL-Divergence, we are fine. Okay, but the problem with KL-Divergence that it's edgy. Mainly, there's some region that no one cares about. It's up in very small probability that things go wrong, and then you're dead. Okay, and you cannot use it. And it's the reason that it's not that. When it works, it's great. When it doesn't work, you have to go back to statistical distance. So I won't get that. Let's just mention that rejection. So now let's go back. What goes wrong with non-public coins? What goes on with non-public coin that you cannot do rejection sampling? For instance, I feel that the verifier is the second. Yeah. Yeah.
So there's, again, saying, so if there's some small probability event that makes the verifier reject negligible probability event in the original protocol, then the KL-Divergence is going to be infinite, because that will happen with the negligible probability in your real distribution, and it will never happen in your ideal.
No, it's fine. It's fine. So it's in ideal, it will no, because you measure according to ideal. In ideal, it always wins. Okay, the ideal, it always wins. Yeah, for in many other cases, but in particular there. So it's not, yeah. So that's quick word why. So we leave the analysis for a second, then go back to it for a very short time. But why this approach does not work for non-public coin protocol, it doesn't work in general, because this random continuation or rejection sampling might be very impossible, actually, for computation-bound entities. And think that the verifier is the first message, commit to a bit B. And then you'd like to do this rejection sampling, you'd like to do continuation of the protocol. If you could, it means that you open the encryption or open the commitment, which you cannot because the commitment is secure, right? So you just cannot do that. What you can do Well, the only thing you can do, at least the thing I had in mind you can do, is assume that this if verifier aborts. If it aborts, well, definitely you can sample in the future because there's no future. Okay? So you sample condition that it aborts. So you manage to sample, but now you skew the distribution. It's not the right distribution. Unless the verifier aborts anyhow, even with very small probability, and then you still skew the distribution, but many hopefully not that badly. And this is what happened with random termination. And let me just say I skip that. I say that what we managed to do. So actually, we try to do the approach of a k-mean and path. And it turns out that to use KL-Divergence, it turns out that KL-Divergence in the setting of this good distribution might be infinite, actually. So you cannot do that. Rather, we consider relaxed version of KL-Divergence. So what relaxed version? We lack some version that is not sensitive to small events. The most natural one, natural approach is to work like when you use smooth mean entropy, is namely to take the infimum over pairs of distribution that are statistically close to the original distribution. This tends to be a bad choice for several reasons. But first, because you are back to using a statistical distance, so you need to understand Q very well, the right-hand side, which you cannot. And second, it does not exploit the, again, or maybe the same reason, different way to express it, it doesn't use the asymmetric way of KL-Divergence. We need to know more about the left-hand side and less about the right-hand side. So what we do, and going to end here, we introduce, I'm sure people thought about this definition, but it works so good for our setting. So I'm not claiming that we invent something new. We're just saying that for this end, it seemed like the right choice. We consider following variant of a smooth KL-Divergence, which again the infimum, we call it epsilon smooth KL-Divergence. Divergence is the infimum over some random function applied to the original distribution, such that this random function first either output the same input or output something outside of the domain. This is some technical part. And the left-hand side function output its input with probability, save at probability epsilon. So we only care what happened with the left-hand side. We totally don't care what happened with the right-hand side distribution. So we maintain this asymmetric property that we like so much, okay? So you only care that with respect to the left-hand side distribution, it's the identity with high probability, okay? And there's nice property that I'm going to skip. We want to prove that the smooth KL-Divergence between the real and this distribution induced by this random termination attack is very small, okay? And I believe that it says something more general about skewed, many routes skewed distribution. I don't have time to explain. Last slide. So we give an optimal analysis of parallel repetition of random termination and partially simulated protocol, and we develop a tool to analyze many round skewed methods. Yeah. Sorry for that. Thank you. Yes.
Can you go back to the definition of the smooth guy? It seemed like you lost any connection to Q in this definition, because you're going, because the FQ can be like anything.
Yes, but it cannot be. What saves us is this fact that either output the original value or it outputs something outside the domain.
So it sounds like it only depends on the support of Q.
Yes, only on the support of Q. Right. Without it, it's nonsense. It doesn't mean anything. But with that, it means, well, you can do whatever you like, but as long if this is small and we know that this is identity without probability, it means that this does not happen. It implicitly implies that because if the KL-Divergence is small and this happens with some probability, that actually this is what is showed here, the Q actually is also the identity with high probability, but you don't have to prove that. Okay, it's automatically by the definition.
Any questions?
Thank you.